Let's think a little bit more deeply about conjugation. Remember that as more and more pi systems become conjugated, the HOMO-LUMO gap shrinks. The energy required to excite an electron from the pi to the pi star decreases or shifts to lower wavelengths of light. So for example, in hexatriene, the lambda max for hexatriene is 330 nanometers, and that's a longer wavelength than, let's say, 1,3-butadiene. Now, what if we were to place these same 6 pi electrons not in a straight chain, but in a cyclic system? We get the molecule called benzene. And notice that the lambda max of benzene is actually much shorter. It's 255 nanometers. And this wavelength is often used to detect or quantify proteins because they contain phenyl rings in one of their amino acids. What this actually tells us is that it takes much more energy to excite an electron from the HOMO to the LUMO. So the HOMO-LUMO gap is actually much greater. This piece of data tells us that there's something interesting going on. Another clue comes from the bond lengths of benzene and hexatriene. So let's say we have this benzene molecule here. We have 2 resonance forms for benzene. And we know that the bond lengths here are 1.39 angstroms, but the bond length here, bond length here is also 1.39 angstroms. And so the double and the single bonds are exactly the same length. But in the case of hexatriene, the single bond is 1.34 angstroms, and the double bond is 1.47 angstroms. Oops, that's the opposite. The single bond is 1.47 angstroms, and the double bond is 1.34 angstroms. And so these alternate between short and long. So in order for the bond lengths of benzene to be exactly the same, we know that we have this resonance form. The Lewis structure is incomplete, so we draw the 2 resonance forms that indicate that the bonds are indeed identical, that they alternate double and single, but what it really means is that they're kind of like 1.5. And sometimes you'll see benzene rings shown like this with a big circle inside. And so we often abbreviate benzene as a 6-membered ring with a circle inside to indicate that the electrons are moving throughout and that all bonds are equal. There's actually a 3rd resonance form for this molecule, which we call duobenzene. And duobenzene has the following structure. It has 2 pi bonds, but then a single bond in between the 2 carbons. So this is called duobenzene. And it makes up about 6% of the resonance contribution. So given this, we want to ask ourselves whether a couple of example molecules are indeed isomers or whether they are the same. So let's draw the molecule 1,2-dichlorobenzene. So we want to know if 1,2-dichlorobenzene with the following 2 resonance forms are isomers or if they are the same molecule. And so it turns out that these 2 molecules are indeed resonance forms of one another. They have the same bond lengths for their double and single bonds. And so we can abbreviate this as a dichlorobenzene system with a circle inside. Indeed, these 2 molecules are identical. But how about another example? So let's do the following example. This is cyclooctatetraene. And we're going to put 2 methyl groups on the cyclooctatetraene. And then we're going to ask ourselves whether or not if we alternate the double bonds, whether these are the same molecule or different molecules. So cyclooctatetraene, often abbreviated COT, one might think that we might be able to draw a circle of pi electrons inside the ring and that there's only one isomer, but that's actually incorrect. COT actually has two isomers, and we say that these are in equilibrium with one another. Right? There is some barrier to activation. It's about 12 to 15 kcals per mole. But what we might not quite understand is why this is the case, why these two molecules are indeed different. If you were to look at the bond lengths for the single bond versus the double bond, they are indeed different. So these are two different molecules. Well, the reason for the difference between 1,2-dichlorobenzene and cyclooctatetraene is a property known as aromaticity. We say that benzene-like molecules are aromatic, and this was originally because these compounds smelled sweet. And we say that compounds similar to cyclooctatetraene are what we call anti-aromatic. Now you might guess that the difference has something to do with benzene having 6 pi electrons, and that the anti-aromatic compound cyclooctatetraene has 8 pi electrons. But that's not entirely the whole story. And we'll come back to how one would predict or define aromaticity in a second. But let's actually try to look quickly at the reactive properties of aromatic compounds, because it is going to confirm that the structures of benzene are indeed special. So let's actually take a step back and talk a little bit about the bromination of 2-butene. So let's say we have 2-butene, and we want to perform a bromination reaction. We're going to treat it with bromine, and we know that we're going to form a bromonium ion, so we can have this set of arrows. We form a bromonium ion, and then of course we trap with bromide anion to give us the trans dibromide. Overall, we lose a pi bond, so that's 63 kcals per mole. But we gain 2 sigma carbon-bromine bonds, and so that's 2 times 67 kcals per mole. So overall, this reaction is exothermic. Now, what would happen if we tried to brominate benzene? If we try to brominate benzene in the same way, we get no reaction. This tells us that benzene is actually a worse nucleophile. Now, this is actually quite strange, right? Because recall when we discussed conjugation, we said that conjugated systems, or more and more conjugated systems, were certainly more stable, but that they were also more nucleophilic. So in other words, this result, where we get no reaction with benzene, is completely contradicting this principle. Now, what if we were to treat benzene with bromine in the presence of a Lewis acid? Well, then a reaction occurs. So let's actually draw out what that would result in. So let's say we take bromine in the presence of a Lewis acid. We could use either iron tribromide or aluminum tribromide. What happens first is that the Lewis acid activates the bromine. So it forms basically a coordinate bond with the metal. And what you end up with is something known as an 8 complex. And so essentially you're going to get a new bond to form in between the bromine and the iron in this case, which kind of leaves a kind of free bromide anion, bromide cation as a really hot electrophile. So this is an 8 complex. And this 8 complex is the thing that is going to react with our benzene ring. So we said that benzene is not as nucleophilic, and so we really need this really strong Br plus in order to get those two molecules to react. So this is really, really electrophilic. And so we get a bond to actually form. And so we get this species here. Now this species can undergo resonance delocalization. And it can undergo resonance delocalization again. Now, in the case of the bromination of butene, we said that we got trapping, we can get a dibromide. Well, it turns out that this doesn't happen here. So we don't get a dibromide to form. We don't get this bromide to attack the atomic p orbital and give us a trans dibromide. That doesn't happen. What happens instead is that the resonance that occurs forms what's known as a sigma complex. So these are the examples of the sigma complex. The sigma complex would actually much rather lose a proton to reestablish aromaticity. So even though this gained a pi bond, this molecule is much, much more stable. So the driving force here is the reestablishment of aromaticity. So this result suggested to those who originally studied it that despite the reaction conditions, there was something special about benzene that made it really a thermodynamic sink. And this turned out to be aromaticity, which is characterized by electrons flowing in a complete circuit in a planar ring. Now, the structure of the benzene ring itself was first proposed by Auguste Kekulé, who dreamt that a serpent was dancing around a 6-member ring while biting its own tail. So what makes benzene so special? What makes benzene so special is the thing known as resonance energy, or what I like to call the aromatic stabilization energy. So let's talk about that next. Okay, the aromatic stabilization energy, or the resonance energy, can kind of be defined if we look at the heats of hydrogenation for various alkenes. So let's actually do this stepwise. So if let's say we have a single isolated double bond. And we wanted to hydrogenate it. So let's say we have cyclohexene, and we hydrogenated it, if you'll recall, with hydrogen and palladium on carbon. We're going to get addition of H2 across that double bond. The heat of hydrogenation here is minus 28.5 kcals per mole. Okay, so if we were to look at this from a reaction coordinate diagram, we can kind of see this as meaning you've got the products are much more stable than the reactants, and the difference in the products and the reactants are 28.5 kcals per mole. Okay. All right, let's take a step up here. So let's go, instead of a single isolated double bond, let's go to two isolated double bonds. Right, so an isolated double bond would be one that's not in conjugation with the other. So let's have those two inside a cyclohexene ring. All right, so if we do a palladium carbon hydrogenation, we get cyclohexane. The delta H naught, delta H of hydrogenation, is exactly double here. So it's minus 57 kcals per mole. And so these are acting like two independent double bonds. Now, what if we were to put those two double bonds in conjugation with one another? All right, so let's do this example. Again, we hydrogenate. We get cyclohexane as our product. The delta H of hydrogenation, and this time, is minus 55 kcals per mole. All right, so it's about 2 kcals worth more stable. Right, so the starting material cyclohexadiene, is actually 2 kcals per mole more stable. We said that conjugated systems are more stable than non-conjugated systems. So this reaction is exothermic, but conjugation adds about 2 kcals per mole worth of stability. So if you're starting from an alkene that is lower in energy, your delta H naught is going to not quite be as exothermic. So now let's talk about benzene. So with benzene, we have 3 double bonds in conjugation with one another. So again, we're going to form cyclohexane. Delta H naught for benzene is minus 50 kcals per mole. Benzene is aromatic, and thus much more stable than cyclohexatriene. One might try to predict the delta H naught by the following formula, right? 3 times minus 28.5 kcals per mole, that's going to equal minus 85.5 kcals per mole. Right, and then if you factor in the contribution from conjugation, you have 3 double bonds in conjugation with one another. So again, 3 times 2 is about 6 kcals per mole. So it should be, if we add those up, about minus 79.5 kcals per mole. However, there's a huge difference between this predicted value and the observed value. Right? We say the observed value was minus 50 kcals per mole. It tells us that mere conjugation is not enough to explain the stabilization. There's something else, there's something greater, and we call that the aromatic stabilization energy. So how large is this aromatic stabilization energy? Well, it's 85.5 minus 50, so 35.5 kcals per mole. And so there's something special about aromatic molecules that can explain a lot of their stability and their reactivity. So how do we determine or predict aromaticity? Well, we follow what's known as Huckel's rule. So Huckel's rule states the following. Things that are aromatic have a closed 4n plus 2 loop of pi electrons that are completely aligned. So essentially there are four factors. The first is that aromaticity comes from things that are cyclic. Things that are aromatic must be rings. The second is that it must be fully conjugated. We cannot have any intervening sp3 hybridized atoms of any sort. You have to have the electrons being able to move around completely in the ring. The molecule must also be planar. In order to align the pi system properly, the molecules must be flat. And then finally, you have to have 4n plus 2 pi electrons in the system, where n is an integer. Or it could be 0. So systems that abide by rules 1 through 3 but have 4n pi electrons are said to be anti-aromatic. If 4n pi electrons, anti-aromatic. So let's do a couple of examples. So we know right off the bat that benzene is aromatic, right? So we'll label it A, aromatic. It has 4n plus 2 pi electrons, where n equals 1, so 6 pi electrons total. It is cyclic, it is fully conjugated, and it is planar. Let's take the case of this four-membered ring, cyclobutadiene. Cyclobutadiene is cyclic, it's fully conjugated. It has 4n pi electrons, where n equals 1, so it had 4 electrons total. So we say that it's anti-aromatic. Let's take the case of the cyclopropenyl cation. The cyclopropenyl cation is aromatic. It's completely cyclic, it's fully conjugated, even though the atomic p orbital there on that top carbon is empty. You can draw resonance forms. So it's completely planar. It has 4n plus 2 pi electrons, where n equals 0. And so it has 2 pi electrons total, and so therefore it is aromatic. If we put 2 electrons into that pi system, it becomes anti-aromatic because now it's going to have 4 pi electrons total. Okay, this system here, the cyclopentadienyl anion, is going to be aromatic. Right? You've got the 4 pi electrons from the pi system from the double bonds, plus 2 pi electrons from the lone pairs, the negative charge. So that's a total of 6 pi electrons. It's completely cyclic, it's fully conjugated, it's planar, and so it is indeed aromatic. How about this neutral species? This neutral species here, the cyclopentadiene, this neutral species is actually non-aromatic, so we'll give it the abbreviation Na. It's non-aromatic because we have a CH2, an sp3 hybridized carbon atom that is not making this molecule fully conjugated. We already said before that the cyclooctatetraene molecule is anti-aromatic. That's because it has 8 pi electrons, which is 4n. Let's take a look at some other types of cyclooctal systems. If we have this system here, this dication has 4n plus 2 pi electrons. It has 6 electrons total. It's completely cyclic, fully conjugated, planar, and so it's going to be aromatic. The corresponding dianion, although, is like this. So this has 10 electrons total, and so again this is going to be aromatic, 4n plus 2 pi electrons. Let's do a couple of examples that are fused together. So now we have 2 benzene rings fused together. There are 10 pi electrons total in that system, again fully conjugated, planar and cyclic, so this is aromatic. And we can extend this further and further and further to give us these polycyclic aromatic hydrocarbons, sometimes known as PAHs. This particular one has 14 pi electrons, and so it's going to be aromatic. And so these 4 factors, cyclic, fully conjugated, planar, and 4n plus 2 pi electrons, these are factors that are easy to remember in determining whether something is aromatic or not. But what is really the reason behind aromaticity, or what is the reason why anti-aromaticity occurs? And for that we need to look at the molecular orbital description, and that will be our topic for next time.